For the block shown in the figure, we need to find the minimum value of P that will disturb the equilibrium. In a two-dimensional plane, the condition of equilibrium for a particle mass is net force in any direction equal to 0. That is, sigma fx equal to 0 and sigma fy equal to 0. This means there is no translation motion. For a rigid body, another condition adds net moment is also 0. This means there is no rotational motion as well. Now let's see what happens when an external force acts on the system. Initially, the friction present between the block and the ground will oppose the translation motion till certain extent. Similarly, the block will resist the rotational motion till certain extent because of shifting of the normal reaction. As we don't know in which case the P is minimum, let's calculate both. Case 1, for translation motion. Here, net force in any direction is 0. So let's calculate along Y, normal reaction acting upwards, a force of 60 newtons acting downwards, give them a sign conventions. On calculating, we get n equal to 60 newtons. Similarly, equating along x-axis, we get P minus frictional force, that is mu n equal to 0. From this, P equal to 30 newtons. Case 2, for rotational motion. The entire free body diagram remains the same except the normal reaction. The normal reaction will shift towards B. Now, why this happens? Assume the block tilts by a small angle delta theta. Now, in this case, the block has only contact at B and the normal reaction always acts along the common normal. Now, as the given system is in rotational equilibrium, summation of moments should be 0. Here I assume the moment in clockwise direction as positive and anti-clockwise as negative. Moment due to P is force P into the perpendicular distance, that is 10 cm. As it's in clockwise direction, it would be positive. Moment due to frictional force is 0 since the perpendicular distance between the force F and axis is 0. Similarly, moment due to normal reaction is also 0. Moment due to 60 Newton force is anti-clockwise, so we may write as minus 60 into 4.5, that is the perpendicular distance from the axis. From this, P equal to 27 newtons. On comparing both the cases, P is minimum in case 2. Here, even if P increases by 0.001 Newton, it will disturb the equilibrium.